Welcome. This problem involves a lake. There's no outlet to this lake, but the lake is fed by a river. The flow rate is 1200 CFS, which stands for 1200 cubic feet of water per second. We have evaporation, and there's a specified rate given, and the surface area of the lake is given by this equation. Goal 1 is the equilibrium depth of the lake. Goal 2 is the river discharge at which the lake will dry up. Next, I'll connect this problem to what I already know. I see a lake, I see a river coming in, and evaporation of water out. The area of the upper surface of the lake, that's this area, will increase if the depth of the lake, that's h, increases. For the second part of the problem, the lake is drying up, so the water level is about 0. Again, the inflow by the river is exactly balancing the outflow through evaporation. The key idea is the surface area of the lake, that's this surface area, is now much smaller because h is approximately 0. This problem looks like it can be solved by applying the continuity equation. The continuity equation says that the rate at which mass accumulates in a control volume is equal to the net rate of inflows of mass minus the net rate of outflows of mass. Since this problem is steady state, the rate of accumulation of mass in the control volume is 0. There's only one inflow, which is the river, and there's only one outflow, which is the evaporation. So it looks like the inflow of mass by the river must exactly equal the outflow of mass by evaporation. I can write that idea with this equation, and of course this is exactly what I can see by looking at my picture. Seems straightforward. Let's get going with the documentation. I document the situation. The river flow for part 1 is specified as 1200 CFS. The evaporation rate is given by 13 CFS per square mile multiplied by the area A. The area A is given by this formula where the depth h is given in feet. I describe the goal. Goal number 1 is the equilibrium depth of the lake. Goal number 2 is the minimum river flow to keep the water in the lake. I generate ideas to reach my goals. I begin by applying the continuity equation. I start this by sketching a control volume. I write the general form of the continuity equation. Since the level of the lake is constant with time, the time derivative of the mass inside the control volume, this term, goes to 0. And when I analyze this term, I get the mass flow rate of the river minus the mass flow rate out through evaporation. So I end up with this equation, and next I substitute known information here and here, and I notice that this equation has my goal in it right there, and all the rest of the information is known. I can calculate the equilibrium depth. I do algebra to arrive at this equation. Then I calculate the equilibrium depth. My calculations show me that the equilibrium depth is 16 feet. To reach goal number 2, I take the same actions I used to reach goal number 1. I sketch my control volume. The continuity equation simplifies to this equation. I substitute for the river flow and for the evaporation, and I calculate a value. Here, the minimum river flow is 58.5 CFS. In review, the continuity equation is super useful. To apply this equation, I select the equation when the problem involves inflows or outflows. I sketch my system and my control volume. I write the general equation. Then I do term-by-term analysis. Lastly, I make sure that my results make physical sense. For example, the physics of this problem were that the inflow of mass from the river equals the outflow of mass from evaporation. In all cases, the continuity equation balances the rate of accumulation of mass inside the control volume with the rate of mass flow into the control volume minus the rate of mass flow out of the control volume. This concludes the example. I hope you have found this very useful. We'll see you next time.